We're stepping away from that traditional Bohr model. We're getting into actually how electrons orbit around the nucleus in an atom, and they do this in orbitals. And we can use the periodic table to start to understand these s, p, d, and f orbitals. And here in this DeBacco University video, I'll cover them each in a little bit more detail. So first off, what are these orbitals? Orbitals are solutions to the Schrödinger equation for electrons and atoms. They describe the probability clouds in not fixed paths each orbital shows here. And each orbital is defined by the principal quantum number, or n, which is the energy level or shell, and then the Azimuthal number here, which is the orbital type. And they see 0 is an s orbital, the 1 is a p orbital, the 2 is a d orbital, and the 3 is an f orbital for completeness. We can see the shapes are very different. So this Azimuthal number correlates with these, and this helps us describe exactly how those electrons are going around. And this is also why we start with the Bohr model, to get you to understand the basic concepts, but now we're getting into the complexities here of how electrons actually behave in these distinct orbitals. So how orbitals shape in the periodic table, as I showed you on that first slide, each element's position on the periodic table corresponds to its electron configuration, especially the outermost or valence electrons. These electrons occupy orbitals in specific order based on energy levels, and we organize them in the periodic table to the s block, which we can't forget about helium, the p block, the d block, and then the f block down here. So it's important to understand when we're identifying these elements where these orbitals are exactly existing, and we can utilize the periodic table to help with that. Now, those orbital blocks in the periodic table, again, how they're defined. The table is divided into blocks based on the type of orbital being filled. S block is the s orbitals, p the p orbitals, so on and so forth. We can also correlate this with the elements. So if we know what family or group we're dealing with as far as our elements go, we can know what orbital shape they will most likely have. So our alkali and our alkaline earth metals are going to have that s block, or in that s block, along with helium. Can't forget about helium. And it's going to have that proper s orbital shape, and we could see that for all the other elements and all the other families. The last electron added to each element is really what determines the block. So really knowing what valence electron is for that element will really help us correlate what to expect. So if we look at these kind of in a little bit more detail, the shape of the s orbital is spherical. Number per shell is basically 1. The maximum of electrons this can hold is 2. It's the highest penetration power because it's the closest to the nucleus. An example would be 1s with hydrogen, or 2s for lithium. The s orbitals are the simplest, most stable due to the proximity of the nucleus. Fortunately, it gets a little more complicated from here. So if we look at the p orbital here, this is a dumbbell shaped, or kind of like a figure 8 shaped. The number per shell would be 3. The maximum of electrons this can hold would be 6. It starts in N2. The orientation is on the x, y, and z axes. So as we're looking at this now three-dimensionally, the p orbitals are directional, which makes them important in bonding, particularly when we talk about covalent bonds. Then we get into the d orbital. This is getting more complex. Cloverleaf or donut shaped. We're really starting to talk in a 3D model here. Maximum of electrons would be 10. Starts at the N3 stage, used in transition metals, coordination of compounds. The d orbitals are critical for metal chemistry, color, as well as magnetism. Now, I'm not going to quiz you exactly on how all of these look, but I do want you to understand that when we're developing these or looking at these different orbitals, developing where these elements are on the periodic table, this just gives you a visual representation of some of those complexities of those electrons. So if we look at that kind of summary table here, again, the S, the P, and the D, we won't get into the F orbital here for sake of not making it too complex. We see the spherical, the dumbbell, and then the clover-leaf shaped here in a nice summary table. Again, we're starting the simplest. As we work our way up, we're getting more and more complex to better correlate or show the probability of where to find those electrons.